This is the question that caused more problems than any of the rest in the homework. I think some of the answers in the back of the book are slightly inaccurate, which may have been the source of some of your anxieties. So I'm going to go through it now quite carefully, and you should get in touch with me if there are any outstanding questions once I've done this. Here we have a glider, which is looping the loop. The picture we've got of it here shows it exiting the loop. So it starts here, and at the start it has both kinetic energy of a half mv squared, which is a half m times 30 squared, which comes out as 450 m. It also has gravitational potential energy. Now, according to the question, the glider is at 700 meters altitude here and 400 here. You can use those figures, but I'm going to cheat slightly in order to make the arithmetic easier. So I am going to call this level here GPE 0. Therefore, its maximum height here is 300 meters, and at the top of the loop, it is going to be at 200 meters, because, of course, the radius of the loop is 100 meters. That will just make the working I do for these two parts a bit simpler. Given those figures, its gravitational potential energy relative to this 0 point here is mgh, which is m, we don't know what that is, g, well, that's just g, times h, 300 mg. We add those two things together and find that the total energy at the start of this motion is 450 plus 300 mg. And we've been told to assume that mechanical energy is conserved. Therefore, the entire energy of the system is that figure throughout the motion. So working out the speed of the glider at the lowest point is relatively straightforward. 100% of that has been turned into kinetic energy. Therefore, we can equate for part 1 at the lowest point, a half mv squared is simply equal to 450 plus 300 gm. We can cancel out the m's, multiply the 2 across and square root, and get v equals the square root of twice 450 plus 300 g. And this comes out as 82.3 meters per second. I think that's the same as the answer in the back of the book. Personally, I would rather call that 82 meters per second, but either one is fine. So that's its velocity at the lowest point in the loop. At the highest point in the loop, not quite so straightforward, because you've also got a bit of gravitational potential energy, in this case 200 mg. So the kinetic energy it has corresponds to the difference between that and that. So a half mv squared is now 450 plus 100 g m. M's go. V equals the square root of that. And I reckon that comes out at 53.5 meters per second. Actually, it rounds down to about 53 meters per second. So those are my answers for its velocity at the highest and lowest points. It's asking for speed. I guess these are horizontal velocities. Okay, speed, same magnitude, same numbers. Now, the magnitude of the acceleration at those points is now quite straightforward, because the acceleration at each point is simply v squared over r. V squared is what's inside the bracket here. So here's my part 2. The acceleration at the lowest point in the curve is simply 2 times 450 plus 300 g over 100. And at the lowest point is 2 times 450 plus 100 g over 100. And at this point, I do differ somewhat from the answers in the back. I reckon that this higher figure here comes in at around about 67.8 meters per second, not 67.2 as I think it is in the book. Although I do agree with the figure at the bottom, 28.6 meters per second to the -2. Those are my answers to parts 1 and 2. This part of the problem is where you have to start thinking very, very clearly about the difference between the occupant of the glider and the glider itself. And to make it clear, I'm going to draw a little picture of a chair. There is the pilot's seat. The pilot is sitting in that seat at the bottom of the loop. That's why it is that way up. Here is the pilot. And that pilot has a mass of 70 kilograms. Therefore, the pilot has a weight of 70 g acting vertically downwards, which means there is a corresponding reaction force of that seat on the pilot of 70 g. But that would be the case even if the glider wasn't moving. But the glider is moving. In fact, we figured out it's really moving quite fast. It was somewhere over 83 meters per second. Therefore, there is another force related to the acceleration required to deliver the circular motion. Now, the other force being delivered by the chair is going to be equal to mv squared over r, mass times acceleration. And that other force is therefore 70 times v squared. Well, if you think back, at the base of the loop, the v squared figure was 2 times 450 plus 300g, and that's over 100. Therefore, the total reaction force of that pilot seat on the pilot is 70g plus all of that. Well, if we work that out, we get a total force of 4746 newtons relating to the circular motion. We have to add that to his weight of 70g. Therefore, the reaction force of that seat on the pilot is 70 times 9.8 plus 4746, which comes out as 5432 newtons. Once again, I think you will find that figure differs from the one in the back of the book. Not by much, but by about 100 newtons. If you just relate that force there to the weight of the pilot is just 70g, which is round about 700 newtons. The pilot's pulling something like 8 Gs there. I don't think that pilot would be feeling very well. So that's my answer for the force on the pilot at the lowest point on the loop. If we now move to the other bit of the loop, that's up here. So now the pilot is upside down. So let's just figure out what's going on here. This time we have our weight of 70g tending to pull him off the seat. Meanwhile, the mv squared over r bit is going to be 70 times 2 times 450 plus 100g over 100, which comes out as 2002 newtons. But this time we have to subtract our 70g from that 2002 newtons. So the normal reaction of the chair, the pilot's seat, on the pilot is now 2002 minus 70g, which I reckon is 1316 newtons. And this figure does actually agree with the one in the answer section. Right, last two parts of the question, I'm going to tackle them together because part 4 is subsumed within part 5 if I do it right. Once I know the maximum radius for a successful loop, I can just write down the answer to part 4. So I'm going back to where I started. Here I have the total energy of the glider at the beginning of its motion as that relative to this GPE0 down here. Now, if I'm talking about an unknown radius r, I have a height here of 2r, therefore a gravitational potential energy at this point of 2r, that's the height, times mg. I want to know what the greatest possible value of r is that keeps this circular motion intact. So what I need to think about is whether or not the acceleration associated with the circular motion is greater than or less than acceleration due to gravity. I need to ensure that the acceleration associated with the motion is at least as great as g. So the acceleration at this point here is v squared over r. That has to be greater than or equal to g. That means that v squared has to be greater than or equal to rg. But I can figure out what v squared is using energy. So that is exactly what I do. I say at this point here, the total energy of the system is, as ever, 450 plus 300g times m. And that is going to comprise a combination of kinetic energy plus gravitational potential energy. And the gravitational potential energy is 2rmg. Well, as ever, I can cancel out all my m's. I can multiply everything here through by 2 to get 2 times 450 plus 300g equals v squared plus 4rg. I can take my 4rg over to the other side, so I now get v squared equals 2 times 450 plus 300g minus 4rg. Now, my critical condition is this one. I now have to satisfy the condition that 2 times 450 plus 300g minus 4rg is greater than or equal to rg, which is equivalent to saying that is greater than or equal to 5rg. I divide through by 5g and find that 2 times 450 plus 300g over 5g has to be greater than or equal to r. That is my upper bound for r. And if I plug in all the numbers, I get something like 138.3 is greater than or equal to r. I reckon r has to be less than or equal to 138 meters. So no, it would not make it round a loop with radius 150 meters. 138 meters is the largest radius of loop this amount of energy can sustain.